everyone. So today we'll be doing chapter 15, just the first few sections. These involve double integrals, and we'll start with doing Riemann sums. And we'll start with this first problem right here, just so you can see it up here, and I can just write bits and pieces on the board. But you remember a Riemann sum from Calc 1? We're going to do another Riemann sum. But we're going to use it to estimate the volume of the solid that lies below a surface. So we used to do a Riemann sum to estimate area under a curve, right? Area under a curve, we build rectangles. So now we're thinking, let's use a Riemann sum to estimate the volume of a solid that lies below the surface of some function like z equal to x cubed y. So that surface may be going like this. So what we're going to do is just build a bunch of rectangular solids and sum up all those volumes. Does that make sense? So it's very simple. It's going to be a Riemann sum. So we have to learn, like, go back and say, all right, we're going to estimate this volume. So we're going to estimate this volume here. Of the solid that lies below z equals x cubed y. Alright, under what constraints? And you'll notice they wrote, here's this rectangle. R for rectangle. Go from 0 to 4 for x, and 0 to 4 for y. So we'll draw that. But when you do a Riemann sum similar to Calc 1, it's like, remember you had a left Riemann sum, right Riemann sum, or midpoint? They're going to tell you which method to use. So in this case they said, use a Riemann sum by subdividing the region into 4 equal squares. And then they wrote 4 regions. M equals n equals 2. Well, I'll write that as let m equal 2, let n equal 2. And I'll show you what we mean by that. That's telling us how many we're going to set up, just like they told you how many rectangles to use in calculus. 1. And they said use midpoints. So they want us to use the midpoint method. So I'm just jotting down some notes from this problem. Use the midpoint method. Use m equals 2. Use n equals 2 when you're setting this thing up. And we're going to estimate the volume of the solid that lies below that surface right there. Imagine what that surface looks like. Now, this isn't going to be the exact answer, is it? Because if you got something going like this, and you stick a rectangular solid to it, part of that solid, like part of it's going to stick out, part of it's going to be underneath it, right? So it'll be an estimation. But midpoint method's still the most efficient, so I can turn that thing off. You know, just so we can concentrate on this problem. Let this camera off. Take that off. And we'll just work this problem out. To work this out, we should definitely draw a grid of this region. I think it really helps. Just draw, this would be the base. There's the x-axis. There's the y-axis. And go on, 1, 2, 3, 4. 1, 2, 3, 4. It's a square region. It could have been a rectangle. That's the base. And we're going to put some rectangular solids in here. And thanks for being patient. Now I can talk about what the heck does this m equals 2 mean. M is for x. They're telling you how many ways you split up the sections here. They want you to split this up into 2 sections. So if m equals 2, that means I'm going to break up this section right here into 2 sections. So I'll just put a line right there. But if this had m equals 4, I would have done 1, 2, 3, 4. All right. The n equals 2 is for the y. In terms of how many ways you're going to split up this. So n equals 2, so I'm going to split it right in the middle. Side of 2 sections going that way. And how many total sections do we have? We've got 4. There's 3, that's 1, that's 1, that's 2, that's 3. So there you go. So all we're going to do is get the volume of this solid coming right here, out of the green board. It's going to hit some surface. And the volume of this solid right here coming out of the green board, and the volume of this solid coming out of here, out of the green board, and this one, add up all 4 of them. So what's the volume of a rectangular solid? That's all we need. That's the only formula we need to do this math problem. Length times width times height. So that's what I'm going to do. We're just going to add up 4 of these. 1, 2, 3, 4. Have this one, this one, this one, this one. All right. How about that little one right there? What's the length and width?
2 by 2.
2 by 2. Or you're 2, you're 2. How about that one? The same? Oh, they're all 2 by 2. So that makes the problem easier. You could factor out that 2 times 2. The question is the height. How far out of this green board am I building this solid here, or this solid here, this solid here, and this rectangular solid here, hitting some surface? That's the surface. Well, they got to give you some method to use. And they said use the midpoint method. And this is why I want you to draw this first. Will you poke a dot in the middle of all those 4 sections? That's the midpoint method. I'm going to put a dot here, a dot here, a dot there, and a dot there. And on those dots, I'm going to label the actual z values. Those will be our heights. All I have to do is use that math formula to find the actual corresponding heights of those points. So, let's see, what's the z value right here? And I'm going to plug in 1 cubed times 1, which is 1. What's the height here? What is 3 cubed times 1? Is that 27? Okay. What's the height here? 1 cubed times 3. So I'm using the x, y coordinates. Okay, is that 3? And then what's the height here? Yikes. 3 cubed
81.
times a 3. What would be the z value there?
81.
81. There you go. I'm going to put this is what the 3, this one was an 81. This one was a 1, and this was a 27. I just sum these up, and then that's the estimate of the volume of the solid. It's not exact, but it's an estimate. Right? It's the midpoint method, so that's usually the best. All from the Riemann sums. Midpoint method is a nice method. In terms of the math, you want to factor out the 2 times 2? I agree. I want to factor out the 4. Now you get 3 plus the 81 plus the 1 plus the 27. 84, 85. What's 85 and 27? 112? All right, what's 4 times 112? 403. That's the volume, but I'm going to write estimated. Estimated volume. Cool. We'll do a couple more of these in terms of estimation, Riemann sums. We'll do a couple more of these because sometimes everyone, in this problem, they just gave you the math formula, right? What if they don't give you a math formula, but you gather some values out of a table, like in terms of like just the heights or depths at certain points of a swimming pool? Well, you could estimate the volume of the swimming pool by this technique. You can estimate the volume of the swimming pool just by breaking it into a bunch of rectangular solids like that. All you have to do is know, well, what's the depth over here? What's the depth over there? We'll do that in a second. Another thing is, this problem they give you the math formula. What if they don't give you the math formula? They give you like contour curves, right? Like a contour map. Okay, then we'll have to read the contour map to get the heights. But they'll still have to give you the method. The most popular is the midpoint method. If you did every problem out of this section, I do want to point out, sometimes they go, use the lower left corner of each solid. So if they said use the lower left corner, I wouldn't have used these. I would have used what? That point, that point, that point, and that point. Does that make sense? Or if they said use the upper right corner. So if they do that in the textbook, you can work every problem out of that in the book in that section. And this is 15.1. Use the upper right corner. Okay, use that point, that point, that point, and that point. Hey, do you remember average value from Calc 1? So average value, you could call it FAADE for average. Didn't we just do an integral in Calc 1, but what did I do out here? 1 over b minus a, and that gave the average. So how do we do this in Calc 3? If it's a function of x and y. So that looks like a function of x. So how can I get the average value of this? First of all, I want to give you the notation for this. You know what you just estimated? We write this as a double integral. We just estimated a double integral. I can call z function of x and y, right? I'll have to put a dy and a dx down there, huh? This is a function of x and y. And here you can put the limits for the y, and here you put the limits for the x. So look at this picture. What were the limits for the y?
0 to 4.
0 to 4. And what was the limit for the x?
Same, 0 to 4.
0 to 4. There's the notation. Did we get this exactly? No, we estimated it, but we estimated this, so we can put a squiggle in front. We estimated that to become 448, just by building 4 simple rectangular solids. Well, then what will this become? It should be very simple. We've got to get the function of x and y's average value. We can write dy dx. By the way, the order of the dy dx and the dy and the dx, or dx and dy, that's something that's going to depend on the problem. You'll choose which way you want to do it. So from here on out, we can write dy dx as just a big dA. How about that? Where a is area. Think of that as dx. dA is dx dy or dy dx. We can use that notation from here on out. This right here is dA. But you might do dy dx or dx dy. I do want to point out, whatever's here is going to represent those limits right there. Should be corresponding to that. So what do you think I got to put out here? It's close to this. But there are 2 b minus a's, right? There you go. So it'd have to be 1 divided by b minus a times another b minus a, which really represents area. So if I call this region right here like D, and what we have to do is it's 1 over the area of D. And I'll just put a D right there. What I'm thinking, there's the region D that you're talking about. The double integrals is representing your region D. You divide out the area of D, and that will give you the average value of that function. So I was just curious if you could estimate the average value of this region right here. Think of these as temperatures. Look, the temperature's 3 degrees here, 1 degree here, 81 degrees here, 27 degrees. Good bless you. Can you estimate the average value of this function? What would I do with that last answer? What's the average value estimate?
Divided by 4.
Yeah, so all I'd have to do is take this average value 1 over and multiply the double integral, which came out to be what? 448, right? 1 over area D times double integral function of x and y dA. So 1 over, what's that area though? Of this whole region.
16.
4 times 4 is a rectangle, it's a square. There you go. Which is, what's that on the calculator if everyone wants to give me, what's that number?
28.
Oh, thank you. It's perfect 28, huh? There you go, that doesn't come out as a decimal. There's the average value of this function over that region. It's averaging 28. But it's an estimate. We're estimating. Cool. There you go. You don't have that function of x and y. I'll take the Calc 1 formula out and I'll leave this up. Here's our first formula. Function's average value if it's a function of x and y. Hey, awesome. We're going to do a couple more Riemann sums, but before we do, can we talk about how to find this exactly? Because we're going to be talking about that today. That comes up in 15.2. You know? We don't have to wait and wait and wait until we do a few Riemann sums. How can we find this exactly? So I'll erase all these, what? I think I've got enough room right here. Let's set it up. Let's find the exact value what goes here? Your function in terms of z. That's your function of x and y. Now, are you okay if I do dy dx?
Mhm.
All right, if I do dy dx, then these have to be the limits of integration for y. And what were the limits for y?
0 to 4.
0 to 4. And for x?
Saying 0 to
0
4.
to 4. But please keep in mind, on this problem, you could have written it as dx dy, because it would have been 0, 4, 0 to 4. And we'll talk more and more about that setup, how you want to set everything up. All right, the way you do this is by iterated integrals. You have to integrate this part right here with respect to that letter. So this is like doing partial derivatives, but you're doing partial antiderivatives. So can you help me out? What's the partial antiderivative with respect to y of an x cubed y? That means x cubed is going to stay down.
So like half of x
So I'll keep
cubed,
that x cubed alone, let it sit, and then I heard it.
half y squared.
There you go. Don't see what I did? I just integrated with respect to y, the x cubed stayed constant. Because I'm doing this part first. Oh, and what were my limits? What do I got to plug in here?
0 to 4.
Now, I sometimes get confused. Are we plugging these into x's or y's? So if you have to, feel free to give yourself a reminder. I'm going to substitute the number 0 into y, and then I'm going to substitute the number 4 into a y.
Ah.
Right? So if you have to label, I know once you get confused, you throw it in the wrong letter. Okay, good. Well, would you substitute those? I'm still doing that inner interval. What's 4 squared over 2?
8.
Okay, 8x cubed. Minus, now substitute a 0.
It'll be 0.
I like zeros. Nice. Now are we done?
No.
They call this an iterated integral. You did the first iteration. Now we're going to do the second.